stuff that's this long.
Sorry?
I said you should get combat pay for reading stuff that's this
I think
long.
we're going to need to be more, but, you know.
One thing I should tell you guys about this homework is that for problem 2, you know, I labeled this problem, what did I say? Infinitely many forbidden minors for representability in characteristic 0. And I asked you to prove 2 things, but those 2 things are not enough to prove that you do have infinitely many forbidden minors. Something that the student in Bogota pointed out to me. And he actually completed the proof, which really takes us a serious extra step. And I would encourage you to look at that in the... I posted solutions, and his solution, that comment is on there. And so you should look at that. He actually came up with a really slick solution, so you should see it.
Oh, yay.
Yeah.
Is that Alex?
It's Felipe. Yeah. So have a look at that. And now we're going to keep talking about Tutte polynomials. So as we were saying, the Tutte polynomial is this really powerful invariant of a matroid. Many invariants that we care about, we can get immediately using that recipe that I wrote over here on the board. Maybe I'll move over here so the camera points this way. So we just said if you have a matroid invariant and it satisfies a recursion like this, a linear recursion that gives you the invariant in terms of the deletion and the contraction, then you have this recipe that tells you exactly what the invariant is in terms of the Tutte polynomial. So that means if we can compute Tutte polynomials, we can get all of these invariants. Today I'm going to show you yet another application of Tutte polynomials. So last time we were talking about applications in graph theory. We talked about chromatic polynomials and we talked about flow polynomials. And now I'm going to show you another application to the topic of network reliability. So the idea is this. Imagine that you have some graph. And let's say that it's connected. And you should be thinking of this as some kind of network. Your favorite kind of network. So you have nodes, and then you have edges connecting the nodes in some way. And the assumption that the graph is connected says that you can go from any vertex to any other one using the edges of the graph. Of course, there's innumerable applications of this. You can think of this as cities and roads, or you can think of this as internet cables, or you can think of this as terrorist networks. This is the hot application where all the money is nowadays, is to hunt down terrorists. So there's a lot of mathematicians that are really studying networks and how to think that each one of these people is a terrorist, and they talk to each other, and then you want to disconnect the network. So that's one of the hot topics nowadays. So any kind of network, okay? And what you're going to think, the idea is to study how reliable this network is. So what's going to happen is that something's going to happen. Maybe some natural disaster, or maybe you bomb the place where the terrorists are, whatever it is. The point is that each edge is going to disappear with a certain probability. So either the road gets blocked, or you manage to break communication between these two people, whatever it is. So with probability P, so each edge fails with probability P.
With the same probability P?
The same probability P.
Okay.
the same probability P. And these probabilities are independent of each other. So whether you broke down this edge has no influence on whether you broke down this edge. These are independent probabilities. And I'm going to just put in parentheses that what I'm going to prove, you can prove another version where the probabilities are different. This also works for different probabilities. Okay. So that's what happens. So maybe this edge broke down, maybe this edge broke down, this one, and this one, and this one. Okay. And now the question you're going to ask yourself is this network reliable? Am I still connected? What is the probability? So let's say that we started with G, and then we got to, maybe we can call it G sub P, which is this random graph where each edge failed with probability P. So what is the probability that G sub P is connected? That's what you want to know. It's a pretty natural question. And, again, you can think of this in both ways. You might want to build a very reliable network so that, even if you have a high probability of edges failing, the network is sturdy enough that this probability is high. In other words, that this is connected. Or you might think of it the other way, that maybe you want to dismantle this network. And the question is, how likely, what probability of dismantling each edge do you need so that you can dismantle the network with a certain probability? Two very, very applied questions. And as we're going to see, they have a lot to do with what we're doing. So what we're going to do now is this. Maybe let's take the graph G. And let's zero in on some edge. So maybe this is the special edge that we care about, and then the graph just goes on. Okay. And so from here, we're going to get this probabilistic graph, G sub P, where this edge might or might not have failed. Okay. So it could look like this with the edge there, or it could look like this. With the edge having failed. Okay, so either E didn't fail or E failed. And of course, we know the probability of these events. This happened with probability. What did I say? P is the probability that an edge fails. So if it didn't fail, that has probability 1 minus P, and if it failed, that has probability P. Okay? So now, I'm only conditioning on what happened with this one edge, but I still have to know what happened to the other ones to figure out if my graph got disconnected or not. Okay? Now, what is the probability that in this situation, in this scenario, what is the probability that my graph is connected, given that this edge failed?
1. No, the probability that it would be.
Now, the other edges might or might not fail, right? So each one of these edges might be there or it might not be there with probability P. The only thing is I'm assuming that E broke down. So E is, it's like it's not there. Okay. So now I need to know if the remaining graph is connected. But if you think about it, really what happened is that I'm just considering the graph where edge E is missing. And then the other ones I'm just deleting with probability P. So this is exactly the same situation as applying this procedure to the graph G minus E, because the edge E is just not there. Okay. So the probability that this happened is 1 minus P. The probability that this happened is P. And what is the probability that G sub P is connected? In this case, and in this case. But like we said, in this case, what happened is that edge E is not there. You can't use it. And so it's up to the remaining edges to find a path, a connecting path. So the probability here is the probability that if I take the graph without the edge E, and then I delete edges with probability P, I get a connected graph. In other words, let me write this as an equation. So, probability that G sub P is connected, given that edge E failed, is equal to the probability that G without the edge that failed is connected after you delete edges with probability P. Okay? So that's the case where the edge E failed. Now let's do it in this case. What is the probability that G sub P is connected, given that the edge E didn't fail? Well, you might guess what the answer is already, and now you have to understand why the answer is. But the idea, of course, is that this is going to be a deletion, this is going to be a contraction. But it makes sense, right? Because the idea is that edge E is there for sure. It didn't get dropped. And so therefore, these two vertices you can think of as the same vertex because you can always go from one to the other one. So the effect of this edge being there for sure is that you do have this path for sure, and you can just contract and then condition over everything else. So this is just the probability that the contraction, when you delete edges with probability P, is connected. So that's pretty cool. That says, basically, I'm conditioning over one edge, and what happens to the rest of the graph is precisely deletion and contraction. It's exactly our dream come true. This is exactly what we wanted to happen. So now what do I say? I say probability that G sub P is connected is equal to, I condition on the variable, I condition on whether E failed or didn't fail. So this is equal to the probability that E didn't fail times the probability that G sub P is connected given that E didn't fail, plus the probability that E failed times the probability that GP is connected given that E failed. And I know what every one of these terms is. In other words, let me give this function a name so I don't have to write this each time. Let me call this the reliability function of the graph with probability P. It's the probability that G sub P is connected Well, what I just proved is that this is equal to the probability that E doesn't fail is 1 minus P. The probability that G sub P is connected if E didn't fail is the reliability function of the, which one is it? The contraction. Plus the probability that E failed times the reliability function of the deletion. Okay. As usual, this is for E not a loop or a co-loop, and for E equal to a loop or a co-loop, you can easily check that this is this what happens, and therefore we can apply the recipe. And the recipe tells us that the reliability function is equal to whatever this says. So here A is P to the, how many elements does the matroid have? Number of edges. Right? This is a graphical matroid. What's the rank of the matroid? Well, remember it's a connected graph. And so a spanning tree has number of vertices minus 1 edges. So I get V plus 1. Then I get B, which is 1 minus P, to the rank, which again is V minus 1. And then I get the top polynomial of the graph evaluated at f of the co-loop. What's f of the co-loop? So you have a co-loop, which means you have an edge connecting two vertices, and now you're going to delete it with probability p. So what is the probability that that leaves the graph connected? With probability p, you disconnected them. With probability 1 minus p, you left them connected. So it's 1 minus p divided by b, which miraculously is 1 minus p. It's not a miracle, of course, but b is the one that you put on the contraction, which is 1 minus p. Comma. Now, f of a loop. So you have a loop connecting to itself, and now you're going to delete that loop with probability p. What is the probability that that vertex is still connected?
What's the probability it's still connected? Oh, 1.
It's 1. It's a vertex. There's nothing to connect. It's connected to itself. Whether you delete the loop or not, the loop is not doing anything. The vertex is already connected. 1 divided by p. And of course, this is 1. So this is my reliability polynomial. This is what I'm going to call it now. I called it reliability function, but it's a polynomial. That's it. I think that's pretty amazing. I mean, that's really a very natural question to ask, and it turns out, again, if you know how to compute the top polynomial of this graph, then immediately you know this probability that the network is going to break down. Now, like I said, if you want to put different probabilities on each edge, then of course there's many variables. There's a variable per edge. And so you're not going to get something so simple because the top polynomial only has 2 variables. But there is a simple way of generalizing this result to say that a slight generalization of the top polynomial can solve this problem for different probabilities. Okay. So that's one thing. And the other thing that I think is interesting about this is that so far, what are the evaluations that we have plugged in? We plugged in the top polynomial at 2, 2, at 1, 2, at 2, 1, at positive integers. Then we actually stretched it a little bit, and If you remember, we plugged in 1 minus q comma 0, and that's what gave us colorings. And that already was kind of weird to take a polynomial, which we were used to plugging in positive integers for. Last time we plugged in a negative integer, 1 minus q, where q is a power of a prime. And we found that, actually, you didn't even need q to be a power of a prime. If you plugged in 1 minus q, for q equal to the number of colors, you got the chromatic polynomial. This time we're doing something even stranger, which is plugging in now not an integer, but some fraction. But you still get an honest interpretation of something that you're interested in computing. Okay. Any questions about that example? Now, I should tell you that, again, this is a field. I mean, and this is just the first result on network reliability, but there's many other questions that you could ask yourself. What's the probability that something else happens? And of course, this is a whole field, and this is just the beginning of it. And if you're interested in learning more about this, I can point you to the right sources. But that gives us 3 very nice applications of Tutte polynomials to graphs. You count colorings, you count flows, and you compute probabilities of your network being reliable. Okay? Okay, so we've done a lot of applications. I'm sure you believe me by now. This is an interesting polynomial, and now that that's clear, then let's actually prove some things about this polynomial. So here's one theorem. The Tutte polynomial of the dual graph, the dual matroid, is the Tutte polynomial of the matroid with the variables flipped. Proof. What's the Tutte polynomial of the dual matroid? It's that summation. Summation of x minus 1 to the rank of the dual matroid minus the rank in the dual matroid of A times y minus 1 to the size of A minus rank in the dual matroid of A. This is the second either definition or theorem, whichever way we want to think about it. But this is the Tutte polynomial. Okay. Now, what is the Tutte polynomial of the matroid? M. Well, it's the same thing, except instead of the dual rank function, you'd have the normal rank function. And so if I wanted y comma x, let me just flip this y and this x. So I get a y here, and I get an x here. Okay? So what I want to show is that these two things are equal to each other. And if they are, the simplest reason to think that is that actually the terms match up. So not only it's true that the summation at the two summations are equal, maybe the terms are actually just equal to each other. And that's what we're going to show. And the way of showing that is basically to just compare these terms. And to do that, we need to remind ourselves of what this dual rank function was. So what was the rank in the dual matroid of A? I had to go look this up. I couldn't remember it. It goes like this. Size of A minus rank of the matroid plus rank of E minus A. Okay. Now, I'm trying to identify this term over here. And this looks to be exactly the right formula. I want size of A minus co-rank of A. Well, here I have size of A minus co-rank of A. This tells me that size of A minus, I haven't said this word, but co-rank is rank in the dual. Size of A minus co-rank of A, this formula tells me that it's rank minus rank of E minus A. So you might be a little bit confused now because we were hoping to get R minus rank of A. We got R minus rank of E minus A. But still, it's R minus the rank of something.
Well, we're going to get everybody.
And you do get everybody.
Just get everybody
Hopefully,
in reverse.
that's what's also going to happen here,
Right.
that this guy is going to give us this one at E minus A.
Right.
So let's check that. What is this? Co-rank minus co-rank of A. Well, you have to remind yourselves of what the rank of the dual matroid is. But remember, if your ground set has size n, and the bases of the matroid have rank r, then the other bases of the dual matroid have rank n minus r. Size of the set minus rank of the matroid. So the rank of the dual matroid is equal to the size of the set, of the ground set, minus the rank of the matroid M. And then I subtract this guy, which is minus A plus R minus rank of E minus A. And of course it works out. Minus R and minus R disappear. E minus A is size of E minus A minus rank of E minus A. So this function is equal to this function evaluated at E minus A. This function is equal to this function evaluated at E minus A. And what that says is that the term of A in this summation coincides with the term for E minus A in this summation. Now, as A ranges over all the subsets of E, E minus A also ranges over all the subsets of E. And so these two things are equal to each other. So that's the proof. That's one possible proof. Can you think of a different proof that we could have done? Basically, the way that this works with the top polynomial is that we have these two ways of thinking about it. One way is this direct way of saying, well, the top polynomial is this polynomial. And so you can just play with that expression over there. The other way we have of thinking about the top polynomial is that it's this recursive thing. And that's the other thing we could have done, is just use the fact that the top polynomial is defined recursively to prove this by induction on the sides of the matrix, because the top polynomial can always be expressed in terms of the top polynomial of the deletion and the contraction. If you go to the dual, that's the deletion and the contraction. And now the deletion of E in the matroid is the same thing as the contraction of E in the dual matroid. And the contraction of E in the matroid is equal to the deletion of E in the dual matroid. I said that too quickly, but the point is you can do this inductively. And this always happens with top polynomials, is that usually you have two approaches. You have the inductive approach, which just says, well, the top polynomial is this magical polynomial that satisfies this recursion. And so as soon as I check the recursion, I'm done. And the other approach is to go directly through the explicit expression for the top polynomial. Okay. So, yep.
I don't know because I just haven't thought about it enough. If you set up essentially, if you set up that the Tutte polynomial of M star, if you show that it's a, what's a Tutte? I was going to say that it's a invariant, but it's an invariant in M star? You know, is there some way of essentially plugging in the right pieces to the Tutte polynomial and showing that you get things switched? Because
That's absolutely right.
Right.
Another proof, which is more or less the same, is to define is to use this universal recipe for any dish that you want to make that involves the Tutte polynomial. You could have defined the function of the matroid to be the Tutte polynomial of the dual matroid. That's a function of a matroid. And you could check that it satisfies this. You could check that it satisfies this. And that means you could plug into here. And when you plug in, what you're going to find is that you just get a y here and an x here.
Because the loops and the co-loops.
Because the loops and the co-loops switch. That's exactly right. So that's another proof. Then you plug it to here. So that's great. That says that the Tutte polynomial behaves as nicely as possible with respect to duality. And this tells us how it behaves with respect to deletion and contraction. Okay, so now the natural question is this. So I'm promising you that this is, the cure to any illness is the Tutte polynomial, right? You can do anything with it. How do you find this polynomial? I mean, do you do this? Do you just plug into this equation? I hope that you did this exercise for the uniform matroid, actually, where I told you could, for the uniform matroid, either plug into this formula or use the tree. The tree is very nice and all, but it only works for small matroids. It's not going to work if I give you a matroid of 100 elements. You would never finish. And if you plug into here, well, you have to evaluate a summation over all the subsets where you have to know the rank pretty well. This could work, or it could just be very difficult. So I'm going to give you another alternative which works better sometimes, often. And again, what we're going to do is count in a finite field. So this is my favorite method for computing Tutte polynomials, and partially it's because it's mine. So I like what you do. So this is in my thesis, and to some, I mean, it's similar to what I told you about the other finite field method. That there was this result that existed in the literature, and people didn't realize that you could use it to compute characteristic polynomials. In my thesis, I proved this method, and I used it to compute a lot of Tutte polynomials, and then it turned out, as I found later, that the statement was, or an equivalent statement was known, but people hadn't really computed any Tutte polynomials using it, or using any other method, actually, because Tutte polynomials are not so easy to compute. So this seems to be one of the better ways of computing Tutte polynomials. And what you do is very similar to what you do for characteristic polynomials. You say you have an arrangement, let's say over Rn or Cn or whatever you prefer, but you need integer coefficients, and then that determines a matroid. If the arrangement is central, and I've glossed over this point several times. If the arrangement is not central, then you don't get a matroid exactly, but you get something that also works. Okay. So what you're going to do is you're going to look at this arrangement over the finite field. Induced arrangement over a finite field. And again, what you do is you just take the equations of your arrangement and you just look at them mod Q. So what did we do last time? Remember, the picture we had was that somehow FQ to the n looked like this grid. I mean, so for example, for x equals 0, this is the example that I showed you. So this is one possible hyperplane arrangement. If you look at it over a finite field, then each hyperplane becomes one of these things. So this is the hyperplane y equals 0. This is the hyperplane x equals 0. And this is the hyperplane x plus y equals 1. And remember what we said last time is that if you wanted to compute, or what we said a while back is that if you wanted to compute characteristic polynomials, then what you have to do is look at this picture and compute the number of points that appear on no hyperplane. Okay. Here we're going to do something very similar, but instead of throwing out the points that are on the hyperplanes, you're going to keep them and you're going to keep track of how many hyperplanes they're on. So you're going to look at each point. So you're not going to restrict your attention to the ones that are not on any hyperplanes. You're going to look at every one of the points, and for each point you're going to count how many hyperplanes it's on. And you're going to say t to the number of hyperplanes is what I want. So h of p is the number of hyperplanes of the arrangement that p is on. Okay. So how many variables are involved here? Well, I have one variable, which is q, the size of the field, and I have another variable, which is t, taking t to the number of hyperplanes. So what the theorem says is that this is basically the top polynomial. So if you compute this, then you have the top polynomial. So let me say basically the top polynomial this is really what you should think. And if you want to know precisely what this says, it says that this is some other polynomial, which I'll define in a second. Some other polynomial, which is basically the same thing as the top polynomial. I'm sorry?
What do you mean by basic?
So I'll tell you what I mean exactly. But what I mean is that this is another polynomial in two variables that if you have this one, you have the top polynomial. If you have the top polynomial, you have this one. So it's equivalent whether you compute this one or this one, because you can get one from the other. What is this exactly? So this is the theorem. And let me define this guy for you. This polynomial in Q and T is just, what is it? It's t minus 1 to the rank times the top polynomial evaluated at Q plus t minus 1 over t minus 1, comma, t. Okay. It's kind of a messy formula, but it says basically once you have the top polynomial, if you just plug in these functions for x and y, then that's this polynomial that I'm referring to here. And the nice thing about this is that, let me now tell you how, this is the recipe to get this polynomial from the Tutte polynomial, but now let me give you the inverse recipe. How do you get the Tutte polynomial once you've done this computation and you've computed this guy? Well, it's basically the same thing. You just plug in something. What you plug in is this. So again, it's another formula that it's kind of messy, but it basically tells you as soon as you have computed this polynomial, you just plug in this on the first variable, this on the second variable, and you have your Tutte polynomial. And so what this method says is just solve this enumerative problem. This is really counting points, and that gives you this polynomial, and then just plug in this garbage, and what you get is your Tutte polynomial.
And the R there is the rank.
And R is rank. So that's why I say basically, the only reason I introduce this notation is so that I can write this in a nice way. So this is just kind of a convenient notation to be able to state this theorem in a nice way. Okay. So let's go ahead and use this theorem. I'll give you an example of how you use it. So let's use it for a specific arrangement. Again, the arrangement consisting of the coordinate hyperplanes. Okay. So I want to compute the Tutte polynomial for this arrangement. Now remember, the idea is the arrangement defines a matroid, and the matroid has a Tutte polynomial. So I want to compute this guy. What I do is basically I say, okay, this is the enumerative question that I'm supposed to solve. Look at all the points in FQ to the n, and for each one of them, count the number of hyperplanes that the point is on, and say t to that thing. Okay. Now, how do you figure out how many hyperplanes a point is on? If I give you the coordinates, how many hyperplanes is it on? The hyperplanes are the equations. Some coordinate is equal to 0. So the number of hyperplanes that a point is on is just equal to the number of coordinates equal to 0. Okay? And so this is not such a difficult enumerative question. You're just saying, for each point in FQ to the n, count the number of coordinates equal to 0. So how many times is this answer equal to k? In other words, what is the coefficient of t to the k? How many times is this answer t to the k? Well, so it's the number of points with t zeros. So how many are there?
You have n spots.
You have n spots. You have to choose where the zeros go.
Right.
So out of the n spots, you have to choose which t of them are going to be zeros. So these are the 0 coordinates.
So wait, quick question.
Yeah?
Why is it t zeros?
K,
K
sorry.
zeros. That's okay.
Thank you. Right, I want to figure out when I get t to the k, In other words, k is the number of coordinates equal to 0. So I want number of points with k zeros. So what I do is I choose which k spots are going to get zeros. And then for the remaining spots, I have to decide what to do. For the remaining spots, I have n minus k remaining spots. And each one of them has to get a coordinate which is not 0. So out of the q coordinates that I possibly have, I have to discard 0, and I have q minus 1 available coordinates. In other words, on each one of the remaining n minus k spots, you have to choose whether you put a 1, a 2, a 3, or a q minus 1. But you're not going to put a 0. Okay. So this is the choice of the other coordinates. Okay. So what I'm saying is that the term t to the k appears this many times. And so this sum is equal to the summation. Now k goes from 0 to n, because I have somewhere between 0 and n coordinates which are equal to 0. And then the number of times that t to the k appears is this one. And choose k, q minus 1 to the n minus k. Does this look familiar? We get really lucky. This is just a binomial formula. And choose k, something to the k, something to the n minus k. So this is just a binomial formula for q minus 1 plus t to the n. And so this is equal to, this is what I just computed, and it's equal to this purple thing. Now, the purple thing, so here's the purple thing. Q to the n minus r. Now, n is n, and what is r? R is the rank of this arrangement, which is just n. You can convince yourselves of that. So I get q to the n minus n, so that's not there. And then I get this guy evaluated at q, comma, t. Okay. So by solving this enumerative question, I found this polynomial. And now using this, I can get the Tutte polynomial. So the Tutte polynomial is equal to, I just have to plug into this recipe over here, which says I should compute 1 over y minus 1 to the r, which I said is n. And then I'm supposed to compute this polynomial, but plugging in this for q and this for t. So I plug in this for q. I plug in y for t, minus 1 to the n. Okay. So what do I get here? The denominator, I get y minus 1 to the n. In the numerator, I can factor a y minus 1 times x minus 1 plus 1, which is x to the n. So what I get in the end is just x to the n. So simple, it almost makes you think that you messed something up. but that's what it is. This is the Tutte polynomial of this arrangement. That's how you use this method. Now, I guess I'll say that for this particular arrangement, it's not too hard to get this answer directly. But there are other arrangements where really the only known way for computing the top polynomial is to do this computation.
And this is because everything is a co-loop. So if you did your tree, you just get a straight line.
What happens is that everything is a co-loop in this matroid. And so the tree is just a straight line of co-loops. Proof of this theorem.
Read your thesis.
Just read, well, either read or no, but really just read. Remind yourself of the proof of the proof for the other finite field method. So we did proof the finite field method for characteristic polynomials. And then it's not too difficult to take that proof and modify it so that it proves this. And modify it a bit. If you want to see, I mean, so the other place to look at this is so I have this paper called Computing the Dot Polynomial of a hyperplane arrangement. And that's where this theorem is proved, and that's where it's put into practice. So this is a good place to see how you actually use this method to compute arrangements. And really, as you'll see by reading this paper, or by flipping through this paper, what you're going to see is that the point is if you get good at counting, if you get good at kind of serious enumerative combinatorics, then you can do these things. And so this is mostly a paper in generating functions and kind of serious computations in enumerative combinatorics, and so you can see what they look like. So this paper is either on the Pacific Journal of Mathematics, or it's also on my website. You can see it there. All right, stop there.
Okay, so I got Ryan for all three of us.
Thank you.
You know Cynthia, Mark's girlfriend? Did you ever meet her?
But I believe you. Mark's up there now, right?
Yeah.
Yeah. Doc was saying, say hi to Mark. Say hi to Dot.
Yeah, Dot will be there. She's in North Carolina, but
She's in North
gonna
Carolina.
be
She's
there.
going to be there. Yep.
Come upstairs to meet you after I teach my class at 3. Is that good?
You're never losing.
Huh?
And I'll be there to meet your guys' flight.
Like it.
What?
I'll see you later.
You know what? I have my other slides. I'll show you. I am 3/4 of the way into LaTeX. And the thing that I couldn't get there on were some of the graphics. But as I was putting it in and thinking about it, there is stuff, like when I went back and looked at it, I'm attached to the graphics. But
I'm gonna go check my email.
they're not, there's stuff that I didn't get to talk about that I'd like to talk
Yeah,
about.
I'll be up in a little bit.
That
so I need to do a couple
could
things,
replace
but
some of
yeah,
that.
probably.
So I managed to scan in a couple of things to like
So,
show what's going on. So we'll see. It depends on how I,